In this next example, we return to social network analysis. This time we're loosely following a tutorial from The Programming Historian by John Ladd and his colleagues. There's a link there if you'd like to read that and see what they did. The data that they collected is the 17th century social network of people who were members of the Society of Friends, or the Quakers as they were rather uncharitably called at the time and still are. Their data comes from the Oxford Dictionary of National Biography, and it's part of an ongoing project on early modern British social networks. We can import both the list of nodes and the list of edges. So here are the nodes. Each one is a person, name of the person, their historical significance, gender, birth date, death date, and ID in the biography. So there are 119 people. Those are the nodes of our social network. And we import the edges from a separate list, and these edges show a link from the source person to the target person, and there are 174 such links. So in this case, the links are listed at least one way. We're not sure if they point both ways or not. Now, as we saw in the Paul Revere example, we can use graph to display some of these. Let me see if I can make this a little better. I don't remember if this worked or not. Oh yeah, that looks a lot better. We can use a graph to display the social network. So here's George Keith, linked to William Penn, George Fox, George Whitehead, and so on. And since the links themselves represent that one person knew another person, it doesn't matter that they're unidirectional in the list of edges, because we are just assuming that if George Keith knows George Whitehead, the reverse is also true. Okay, so if we plot this whole collection of relationships, we see that there is a large component that connects a lot of people to one another, but there are also a lot of smaller networks that consist just of 3 people or of 2 people. So this entire social network isn't connected, at least in the data set that we have. It consists of separate components. There's a command called connected components, which gives us lists of each of the people in each of these components. So if we start with one of the smaller ones, let's say right here, this is just 2 people who know each other. This larger list that starts here, ends with William Gibson and starts with Joseph Bess, that larger list is all of the people in this large connected component in the center. Now the number of connections to a particular vertex, or a particular person in this case, is known as the degree. And we can scale the size of the nodes so that it reflects the number of connections. So this person here has lots of connections, so they get a very large node. The little people out on the end who only know one other person have a smaller node. And the people who only know a few people, again, have smaller nodes. Another thing that we could do with visualizing our graphs is we can start to think about things like the density of the graph. So I'll just read the definition to you. The density of the graph is the ratio of the number of actual edges divided by the number of possible edges in the graph with the same number of vertices. So we could say the number of actual edges between people is 174. The number of total possible connections is more than 7,000. So about 2% of these possible connections are actual connections. We can also measure what's known as the distance and the diameter of a graph. So the length of the shortest path between any 2 vertices is the distance. We could say, what's the distance between Margaret Fell and George Whitehead? 2. What's the shortest path? We can ask for Mathematica to find that actual path for us and say, well, what's the path between Margaret Fell and George Whitehead? In this case, it turns out to be William Penn. So in the idea, if you think of a network as degrees of separation, William Penn is the degree of separation between Margaret Fell and George Whitehead. We can ask for the graph distance for all of the connections for Margaret Fell, and now this is simply the list of people, distance 2, distance 3, and so on. You'll notice that there are some infinities. If she's part of that large connected component, she doesn't know anyone who could introduce her to the people who are in the pairs or triplets, the much smaller networks. We can also talk about what's called transitivity. So if two people know a third person, it's also likely that they know one another. In the case of Margaret Fell and George Whitehead, they both know William Penn, but they don't know one another. The graph looks like this. In the case of George Whitehead and George Fox, they both know William Penn, but they also know each other, and when that happens, instead of a straight line network like this, you end up with a triangle. And we can measure this property of the network with what's called the global clustering coefficient. And once again, that gives us a number that we can use to compare this network with comparable networks, or that we can look at, say, over time. Does this increase or decrease over time? What does that tell us about the social relationships in this particular group? In the Paul Revere lesson, we looked at some measures of centrality. And in this network, we can again compute the degree centrality. That's this one here. George Fox has the highest, then William Penn, James Naylor, and so on. There's also a measure called eigenvector centrality. Let me read this again from the tutorial. Ladd and colleagues note, eigenvector centrality cares if you're a hub, but it also cares how many hubs you're connected to. The closer to one, the greater the centrality. So this measure is useful for understanding which nodes can get information to other nodes quickly. If you know a lot of well-connected people, you can spread a message very efficiently. And we can see by this measure, George Fox has the highest eigenvector centrality, just as he had the highest degree centrality. But William Penn has dropped from second place to third place on this particular measure. And finally, we can use betweenness centrality to help us find brokers, and these are people who connect otherwise separate parts of the network. William Penn is the highest by this measure, and then George Fox. Now, we can also pick out pieces of the graph and measure properties of that. So for example, this next expression here selects out the women in the data set, and we can measure betweenness centrality just for the women and not see that measure for the other men, or for the other members, who are men. So if we have data about the various nodes in our data set, or the various persons in a social network, we can use that information to construct queries of various kinds. Since we have their birth dates and death dates, we could also use it to extract information about people's ages and perhaps do something with that. Now, if a group of people in this case are vertices in general, are densely connected to one another but relatively loosely connected to other vertices, then we're going to call that a community. And the command community graph plot shows us, if we take that large connected component, it shows us that it actually is broken down into 7 components, or 7 communities in this case, not components. And we can use the find graph communities command to see what each of those components is. Communities in that component is. And once again, we can use that information to characterize the society, to characterize the social networks and the relationships that people had at the time, and perhaps use that to investigate other things or to frame other kinds of research questions.